So let's pick up where we left off. We can use the empirical rule from time to time. So keep that in mind if you have something where the numbers fit the empirical rule, and that's why drawing a picture is really helpful. Now, what if we need to figure out what number produces a certain probability? In other words, what measurements produces a certain probability? So it says sometimes we are interested in finding the value for a random variable associated with a given probability. So the question says find k for which the probability that x is less than or equal to k equals 90%, 0.9, given that we have a normal distribution with a mean of 70 and a standard deviation of 10. So I'm going to make a quick picture of what this would look like, and I want you to do the same thing. So we've got our normal distribution. We know that 70 is in the middle. So they want the probability that x is less than some number k to be equal to 90%. So before we put k on the graph, I want you to think about what side of the 70, what side of the mean would k need to be on in order for the probability below it to be 90%. Think about that for a second because that's a really important thought. If I were to put k over here and I want the probability below it to be 90%, I'm shading in this region. Does that look like 90% of the graph? No, certainly not. So it's not going to be on that side. Half of the graph, remember the halfway point is where the mean is. So half of the graph, the area is to the left of the mean. That'd be 50% of the data. I want 90% to be to the left of this particular number. So that means my k value has to be somewhere pretty far out to the right side of the mean. So again, think about that. I want 90% of the data to fall below this k value. So my k value has to be out here, and 90% would be the region that I'm shading below that k value. So the way we can figure this out, we can actually do this in StatCrunch. If it's an empirical rule question, of course, we could use that, but this is not. We want 90% of the data to be below that particular number. Our question is, what is that number? So let's go ahead and let's look at how we would do this in StatCrunch. You're going to go to Stat, Calculators, Normal, just like you did before. Select Standard again because I don't want to be between two numbers. I just want to be below one particular number. Be sure you tell StatCrunch put in the mean of 70 and the standard deviation of 10, and I'm actually doing this with you. And then in the line below where it says P of x is less than, this little section right here, since that's what we're trying to figure out, you're going to leave that blank. You're literally going to leave it blank in StatCrunch, and then to the right of it, you're going to put equals 0.90 because you want that probability to equal 90%. Click Compute. And you should have a picture that looks very similar to the one we have. And in the picture, it'll say something like this. The probability that x is less than or equal to 82.8, looks like 155, something, equals 0.90. So what they're telling you is that if you are below this number of 82.8, your probability is going to be 0.90. So my answer, we could say that k, however they tell you to round it in StatCrunch, of course, I'm just going to say 82.8. And does that make sense? We said that the k value had to be to the right of the 70, so 82.8 certainly is. Let's look at our seal pups example again. Suppose the birth lengths of newborn seal pups follow the normal model. And again, the first number is your mean and the second number is your standard deviation. Suppose pups with lengths at the 15th percentile and below are unlikely to survive. What birth lengths would make it unlikely that a pup would survive? Let's make a quick sketch of it first. All right. So in the middle, I'm going to put my mean of 29.5. And think about what this means. If you're at the 15th percentile, that means you are above 15% of the data. So we're looking for the number so that x, if I'm less than or equal to whatever that number is, I'll call it k again, I want that to be 15%. So the 15th percentile means you're greater than 15% of the data. So your data would be less than that number. The data less than that number would be 15% or 0.15. Where is that going to be? If I only want to cover 15% of the graph, am I going to be to the left of the mean or am I going to be to the right of the mean? That's a really important thought to have. 15% is a really small probability. So it's going to have to be somewhere over here, right? There's going to be our value. Here I called it K, so let me stick with that. I use that K again. So that's the number we're looking for. And then we want to the left of that number, we want that amount to be 15%. And that's what we're saying. So everything's opposite now. Instead of giving you the number and asking you for the probability, I'm giving you the probability and asking you for the number that would have produced it. So you're going to go into StatCrunch. You're going to follow the same directions, stat, normal, stat calculator, and then normal. I'm going to go ahead and do that on my computer. And then you're going to make sure the standard button is clicked, put in the mean and the standard deviation, and then enter P such that X is less than or equal to, and leave that blank, and then put in 15% for your probability. And you should get a picture that looks similar to what I have. And I'm getting, see, StatCrunch is giving me an image that looks like this, 26.908 something something equals 0.15. So the number I'm interested in is 26.9. So any seal pups that are born that are below 26.9 inches are unlikely to survive because they would be at that 15th percentile. Oh, here's a picture of it right here. So this is what the screenshot from StatCrunch would give you. And so that number that you want is right there. Okay, so the next example. Suppose the amount of money people keep in their online PayPal account follows a normal model. Consider these two situations. Identify whether the question is asking for a measurement or a normal probability. So the probability is that area, right? The probability is what's shaded in red. When they say measurement, they're talking about the number, the X value. So they're asking which one are they asking for in each of these respective questions. Part A says, a PayPal customer wonders how much money he would have to put into an account to be at the 90th percentile. 90th percentile, that means you're at 90% of your data. 90% of your data is below this particular number, how much money he would have to put in. So what are they looking for in that case? They're giving you the 90th percentile. That's your probability. Instead, they are working backwards, and like in that last question, and asking you for the measurement. Part B, a PayPal employee wonders what the probability is that a randomly selected customer will have less than $150 in his account. So that time they're looking for a probability that a randomly selected person would have less than $150 in his account. So in that example, they're looking for the probability or the percentage. Same thing. Okay, the standard normal distribution. Now we haven't talked about this yet, although we did talk a little bit about z-scores earlier in the course, and it's all the same idea. The standard normal distribution is a special normal distribution that has a mean of 0 and a standard deviation of 1. The total area under its density curve is 1, just like any other normal distribution, so that part shouldn't be new. Therefore, the standard normal distribution has z-scores on the x-axis as illustrated below. So this would be the example of a standard normal distribution. Your mean, you notice, is at 0. The standard deviation is 1. So we've got 1, 2, 3 standard deviations above the mean, 1, 2, 3 standard deviations below the mean. And so those are what we call z-scores. So the first question says, find the probability that a z-score is greater than 2.31. So the probability that z is greater than 2.31. Locate the value of 2.31 on the x-axis above. So this is the same stuff we've been doing. They just want you to go ahead and go through the steps of drawing the picture again. So 2.31 I'm estimating is maybe right about there. So I'm going to go ahead and call that my z-score because we're on room. And then it says, let's see, draw a vertical line. So there's my vertical line. Since we would be concerned with the area greater than z, since they want greater than 2.31, we're going to be on this side. Okay, so we're going to be on this side. Lightly shade to the right of the vertical line, and then using StatCrunch, find the area. So in StatCrunch, it's the same procedure we've been using. You're still going to go to your normal distribution. So you're going to go to Stat, and then Calculator, and select Normal. You're going to click on Standard. The only difference is that your mean is going to be 0, and your standard deviation is going to be 1. And then you want it to say, so let me here, I'm going to draw another picture down here. So you want it to say, here is 0, here's 2.31. We're looking at this way. So you're looking at the probability that X is greater than, and I'm using X because I'm talking about StatCrunch, and they default to the variable X. They use Z, it's the same thing, it doesn't matter. So we want greater than 2.31 in the computer, and I'm getting a value of about 0.010. So, about 10% if we want to write it as a percentage. Using the same steps above, answer the following questions and sketch a region for each one. Okay, so find the probability that Z is less than or equal to negative 1.25. And by the way, I want to just mention also, when you say less than or equal to or less than, it's the exact same thing when you're talking about a continuous distribution. So if I wrote it this way, it's going to be the exact same thing. Whether I actually include the 1.25 or not does not matter, because the area is an area under a curve. And I can't have an area at a specific point. That wouldn't make sense. So whether you include the equality to or not, it makes no difference. StatCrunch by default does, but it does not matter. All right, so I'm going to do the same thing. I'm going to go into StatCrunch. I'm going to shade this first so I know what I'm looking for. Notice my z-score was negative, so I put it on the left side of the graph. And you should kind of estimate what you think the number should be. It should be a fairly small number, because negative 1.25 would be 1.25 standard deviations below the mean. And according to StatCrunch, I'm getting about 0.106. Run through it with me and make sure you get the same thing. Now, part E, it says find the probability that Z is greater than or equal to negative 1.25. I can draw a picture again. It's going to be similar to the picture right above it. So negative 1.25. But the difference is, instead of shading to the left, I'm going to shade to the right. So what you want to think about is, how are the question in E and question in part D related? It should be pretty clear that this is the complement. Remember, we talked about the complement earlier in the course. Greater than negative 1.25 is the same as the complement of less than negative 1.25. So since these events are complements of each other, then to find the complement, remember, we can just do 1 minus the probability above it of 0.106. And so let's see what that gives me. Let's see, 1 minus 0.106. I'm getting about 0.894, and that would be the complement of the 0.106 in the previous example. How about in letter F? So let's see, I'm going to make some space here. I'm going to erase some stuff just so I have some more space. All right, so in letter F, they want us to find the probability that Z is between negative 1.96 and positive 0.196. So 0 is in the middle, negative 1.96, positive 1.96. This is symmetric on either side, so the areas on either side of 0 should be about the same. But then now we're back to a between probability. So when you go into StatCrunch, make sure you change it to the between at the top instead of standard. And so my lower bound is negative 1.96, and my upper bound is 1.96. And I'm going to click compute, and I'm getting about 0.95. And actually, this should look familiar to you. 95% of the data. Remember, the empirical rule says that about 95% of the data falls within 2 standard deviations. And that's really what we're looking at here. Okay, negative 1.96, that's about negative 2 standard deviations if we ballpark it. 1.96 is about 2 standard deviations. So we should expect to get about 95% of the data. All right, so then the last question, it's saying, what is the probability of getting either less than negative 1.96 or greater than negative 1. Or positive 1.96? So that would be, again, the complement. Let me try to make my graph look a little bit better here, a little bit more symmetric. That would be the complement of the above event. So if 0 is here, negative 1.96 is here, positive 1.96 would be here. So less than negative 1.96 would be this end of the graph. Greater than 1.96 would be this end of the graph up here. Those are the tails, or the opposite of what we saw in the previous example. So in the previous example, we wanted the area between those two numbers. Now we want the extremities on the outside of those two numbers. And so since those are complements, I'm not going to use StatCrunch to do this. I'm going to instead just do 1 minus the 0.95 that we previously had. So there's about 5% chance, 0.05, that a z-value, a z-score would be less than negative 1.96 or greater than positive 1.96. All right, let's take a look at the next example. It says IQ scores for all humans are normally distributed with a mean of 100 and a standard deviation of 16. So first, what symbol do we use to represent the value 100? That's our mean, so we can say mu equals 100. The value of 16, that's our standard deviation, so we'll say sigma equals 16. Suppose someone has an IQ score of 80. Right, what proportion of the population has an IQ score lower than this? So we're looking for the the probability that a randomly selected person is less than 80 for their IQ. So let's make a quick sketch, and then we're going to probably use StatCrunch to do this unless we can use the empirical rule. So 100 is in the middle. One standard deviation below, that would put me at about 84, it looks like. So we want to be at 80, so we're a little bit past one standard deviation. So I'm going to put an 80 right there. And we want below that, so we're looking for this little area in here. Try to think about what should that be, what makes sense. It should certainly be less than 50%, right? Because it's less than half of the graph. And, 50% seems a big number. I'd say it's probably less than about 30% of the graph. Let's go ahead and take a look. So the mean was 100, standard deviation was 16. And we want to be below a score of 80. So from StatCrunch, I'm getting a value of about 10%, 0.105. Sorry, my phone keeps buzzing. 0.105 again. So about 10%. We could have converted this to z-scores and calculated it the same way, but using a standard normal distribution. And one comment I want to make. I know when you're doing the assignments in StatCrunch, if you click on the help, a lot of times they convert them to a standard normal distribution. So like a question like this, it might have said define the z-score and then figure out the probability that we're below that z-score on a standard normal distribution. That is not necessary. There's no reason that you have to convert this to a z-score unless the question explicitly tells you, or like in the next question, if you're trying to compare two different distributions, there's no need to convert it to a z-score when you can just put everything into StatCrunch. So let me show you an example of when a z-score would be useful. So Kelly scored 73% in history, where the class mean was 68% and the standard deviation was 10.2. In mathematics, she scored 66, where the class mean was 62 and the standard deviation was 6.8. In which subject did Kelly perform better compared to the rest of the class? So when you're comparing distributions, absolutely, that's when you want to go ahead and compare z-scores. So the formula, this was from Chapter 3, the formula we had back in Chapter 3 looked like this. So to convert a z-score, we said x was equal to x minus x bar divided by s. And remember that x bar was the mean for a sample, and s was the standard deviation for a sample. We're gonna upgrade this formula just a little bit, and now we're going to use, instead of x bar and s, we're going to use mu, because we're talking about a population that's normally distributed. So we're going to say x minus mu divided by sigma. And so I want you to see these are equivalent formulas. Which notation you use doesn't really make a difference, but we're going to use the second notation when we work with this because we're looking at a normal distribution, and it's a population now instead of just a sample. So let's go ahead and calculate her z-score. So her z-score for her history class, her test in history was 73, and the mean in the history class was 68, and the standard deviation was 10.2. You could convert these to decimals, but it's not necessary. As long as if you convert them to decimals, you do it for all three numbers. But I'm going to leave them the way they are because it's really not necessary to make that conversion. And so let me get my calculator out. I've got 73 minus 68 divided by 10.2. I'm getting a z-score of about 0.49. Notice it's positive. It should be positive because her score was 73, which was above the mean. Remember, when you're above the mean, you have positive z-scores. So that means she scored better than about 1.49 standard deviations above the rest of the class. All right, let's take a look, or above the mean, I should say. Let's take a look at her math score. So in math, her score was 66, and then the mean there was 62, and the standard deviation was 6.8. So let's go ahead and compute those numbers. So let's see, divided by 6.8. I'm getting a z-score of about 0.59 if we round it. So she did better than the rest of the class, about 0.59 standard deviations above the mean. So which class did she do better? We could think about it visually. If we looked at a graph, 0.49, if we put that z-score 0 here, put 0.49 here, above that number, she would have scored better than everybody else. And the probability would be shaded region here that somebody scored below a 0.49. For the other group, and actually, well, here, I'll tell you what, instead of doing a separate graph, let me do it this way. Let me put the math graph on the same graph but a different color. The z-score for math was 0.59. So the probability that somebody did worse than her in the math class would be all of this region. Okay? So by that comparison, which class did she perform better in? Her math score was lower, but compared to the rest of the group, she outperformed a higher probability of students in her math class than in her history class, because this z-score is higher for math than it is for history. So we can say that she outperformed everybody in her math class since she had a higher z-score. That's probably the simplest way to say it.